Last time we had talked about section A3, solving these systems algebraically. And I asked you guys to work on 9 through 18. Let's start with questions from that, or previous homeworks is fine. Landon?
Can you do number 7 from
Sure. So 7 is x is greater than or equal to -8. Y is less than or equal to -1. And then y is less than -2x minus 4. So here we're solving a system of inequalities. I noticed right away all of these are in the proper form, so I don't have to do any rearranging. So I'm just going to generate some points for each of these. So for an x equals equation, actually we pretend they're that, the x has to be -8. And since there's no y in the equation, y can be whatever it wants. For y equals -1, again, the y has to be -1, and because there's no x, x can be whatever it wants. And then my last one here, let's say pick x to be 0, so y would have to be -4, or x to be -1, so y would have to be -2. So let's go ahead and start drawing some stuff here. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 1, 2, 3, 4. All right, so let's do blue, and then green for this one, and gray for that one. So because this is a greater than or equal to, I'm going to draw a solid line. Because this one is a less than or equal to, I'm going to be drawing a solid line. And then for the last one, so 0, -4, -1, -2. For this one, it's strictly less than, so I'm going to be drawing a dashed line. And now let's look at the shading directions. I'm not going to draw the shadings. I'm going to just use a little arrow for right now until I figure out where the overlap is. So greater than means I'm going to be shading above the line, or in the case of a vertical line, it really means to the right. The green line, it's saying shading below because it's a less than, and the gray line, it's shading below. So we're talking then about below the green line, below the gray line, and to the right of the blue line. So we're talking about like that area in there. Alex? Sure. Landon, does that feel okay?
Yeah, I messed up the shape.
Okay. Again, it's just a matter of like making sure you fit all the, you're in between all the lines or whatever. Anybody else? Okie dokie. Well, let's finish things up then for today. Section A4, we're just going to be looking at 3 variable systems and solving those. Just find my page here with my examples. So a 3-variable system is basically, or a 3-variable equation, excuse me, is something that looks like this, where the x, y, and z are our variables, and the a, b, c, and d are our constants. And obviously for this to be an equation in 3 variables, that a, b, and c can't be 0. Because if one of them was 0, then it's an equation in 2 variables, or if 2 of them were 0, it'd be 1 variable. So our solution then is going to be an ordered triple. So typically we order them in alphabetical order. If our variables were x, y, z, our solution is going to be the ordered triple, or the point x, y, z. And that point would have to satisfy the equations involved. And just like before, we can have 3 types of solutions. You can have one solution. You can have no solution. And we can have the infinitely many solutions. And in that case of infinitely many solutions, there's a little bit more to that than with 2 variables that we're going to ask you to do, but we'll cross that bridge when we get to it in the example. To solve these things, we're really only going to be looking at 2 methods. We don't use graphing to try to solve a 3-variable equation, because with 3 variables, your graphing would have to be in 3 dimensions then, and that's not trivial, and graphing a line in 3 dimensions. And certainly your calculator can't handle that, so it just becomes really not a very useful technique for us. Instead, we're just going to be concentrating on the algebraic techniques we talked about last time, that being substitution and elimination. And those 2 methods work largely the same way that they have before, except there's like more substitutions you have to do or more eliminations you have to do. It's just because there's an extra equation, an extra variable, there's a little bit more to do, but it's the same basic pattern. So let's just look at a couple of examples. Sound okay? Okay, so let's say we have the system 4x plus 2y plus 3z equals 1, 2x minus 3y plus 5z equals negative 14, and 6x minus y plus 4z equals negative 1. So if we're doing substitution, which is what we're saying we're going to do in this example, the first thing that I'd want to do is I'd want to decide which equation and then which variable in that equation I want to get by itself. Now, there is no wrong answer to that question, but oftentimes there's a best answer in terms of making your life a little bit easier and avoiding fractions and that kind of stuff. So if I look at this system, which variable and which equation would be the one that I would want to choose to make my life the easiest? Any ideas? What do you mean by the first one?
So like which variable?
Which equation and which variable would I want to choose to get by itself? Right? Because we need to do that. Jack? Yeah, the y in the third equation. And that, I think, makes life easiest because I know since there's no coefficient, I never have to divide by anything and create any fractions, which is basically what I'd like to avoid if I can, right? Not that the fractions make the problem undoable, but they're a hassle, right? And if I can avoid having that hassle, I'm going to take a minute and be careful here and see if I can avoid that. So for this one, I'd start by subtracting the 6x over and the 4z over, and then divide by the -1. To get the y by itself. Now that y is by itself, I'm going to take what y equals and substitute it into the y's in the other two equations. So everything else is going to stay the same, except in place of y, I'm going to write 6x plus 4z plus 1. And then I'll do the same in my other equation. Any questions as what I've done so far? Okay, I'm just going to go ahead and simplify things in these two equations now. So I'll distribute my 2 through. Oops. Guess I should write that a little neater. Then if I group my x's together, I have 16x. I group my z's together, I have 11z. And I'll subtract this 1 over to make -1. And we'll go ahead and do the same thing on the other side. I'm going to make sure that I take the negative with the 3 along with me when I distribute, though. Easy to forget to do that. If I group those together, I have -16x, -12z, and 5z is -7z. And if I add the 3 over, I get -11. So what I have now is 2 equations in 2 variables. So that first step that we did with the substitutions, we were able to eliminate 1 variable in 1 equation, and now we have a 2-variable system with 2 equations in it. Is everybody okay with that? Yes? Sure. At this point, we have choices. We can either solve this 2-variable system that we've just created. We could continue using substitution, or we can use elimination. Which one appears to be easier at first glance? Elimination. Why? Yeah, the x coordinate or the x variable is already set up to be eliminated, right? That's lovely. Let's do elimination, because we're all set to go. Because all we need to do is add the 2 equations together. And we will be in a great spot And if we see an opportunity to make our lives easier, whoo, doggy, let's take it, right? So I add the two together, I get 4z equals negative 12, and divide both sides by 4, I get negative 3 for z. Feel okay there? Now that I have one solution, I'm going to take that back to any two-variable equation and plug that in. So I guess I'll just plug it into the first one, I suppose. Maybe I'll write it up. Yeah, whatever. It's fine. So 11 times negative 3 is negative 33. I add 33 over, and negative 1 plus 33 is 32. Divide both sides by 16, and I get x is equal to 2. So now I have x equals 2 and z equals negative 3. So I'm going to take these two answers and go back up to any of the three variable equations that we had written. The one that I would pick would be the one where the y is already by itself. So now I have y equals 1, x equals 2, and we had z equals negative 3. Oops, forgot my negative. Or we'd write our final answer as the order triple x, y, z. And that's my final answer. So you notice these can get kind of long, right? In my experience, one of the things students struggle with the most on problems like this is just kind of staying organized and keeping track of where they're at in the problem. So if you are someone that's not naturally organized or is kind of all over the place with your work, that's something that I would caution you about and try to stay organized. Like build a little walls on your problem. Like once you finish one part of it, like block that off. Start working on the next part so that it's easy for you to kind of keep track of what you've done and what you still need to do. But that's going to become, or tends to be, a challenge for some students. Everybody okay so far, though? Again, much different than what we did in the two variables? Not really, right? Same stuff. And in reality, the first step is to just get a two-variable system that we can use the last lesson's techniques on directly, right? Let's do an elimination example. So 3x plus y minus 2z equals 10. 6x minus 2y plus z equals negative 2. Then x plus 4y plus 3z equals 7. Okay, so this one we're going to use elimination on. Again, when we use elimination, the first step would be to pick a variable to eliminate. Again, it doesn't matter which variable you choose to eliminate, although if by being careful, you can sometimes make your life easier. Now, if I look at this particular problem, I see that for every variable x, y, and z, I have a variable whose coefficient is 1. That basically tells me that no matter what, I can make this pretty easy to do the elimination. So really, even choosing x, y, or z, there's not really a difference. They're going to be equally easy. Do you guys see that? So let's just say, for the sake of argument, we chose x. Cool? All right, so we'll call these guys equations A, B, and C. Basically, what my plan is going to be is I'm going to use the equation C to eliminate the x's from equation A. And then separately, I'm going to use the equation C again to eliminate the x's from equation B. That'll result in two variable equations, and I'm back to a section 3 problem. So what if I want to eliminate the x's in equations A and C? What do I need to multiply equations A and C by? Close with 3. It's actually, though, -3, right? The signs have to be opposite because we add them together, they have to cancel out. So equation A can stay the same, but equation C needs to be -3. And then we're going to do the same thing with equations B and C. So what do I have to multiply by here? Yeah, equation B just stays the same, and equation C gets multiplied by -6. Cool? Okay. So let's go ahead and write that out so we can do our adding. So -3 times C gives me -3x, -12y, -9z, and then -21. Don't forget to add or multiply at that very last term at the end. Frequently, I'll see students forget to do that. Okay. Then do the same thing over here. So there's B, and then -6 times C gives me -6x, -24y, -18z, and then -42. So it's going to be -26y minus 17z equals -44. So I take these two guys and make myself a new system. And I got kind of a yucky looking system here, right? So, I mean, you could do something like multiply, if we call these guys again, we'll call it A and B. We could multiply A by like -26 and B by +11. And that'll work, but the numbers get kind of big, right? Substitution's going to be just as lousy because you're going to have fractions all over the place when you try to isolate a variable. But I want to draw your attention to one thing here. Look at the coefficients in this equation. Did you notice something about them? They're all -11, right? So what if I just divide both sides of this equation by -11? Come on. That makes the elimination a heck of a lot easier on the next step, right? Will you always be able to do something like that? No. But if you notice, that you can do something like that and makes your life easier, feel free to go ahead and do it. Almost always, if you can make the coefficient smaller, the problem usually gets a little nicer. You know what I mean? So that's a nice little trick that you can tuck away and put into your toolbox. You know, that doesn't happen too often, but when it does, like here, it makes the elimination at the next step quite a bit easier now, right? So it doesn't really matter whether you eliminate the x's or z's, or I'm sorry, the y's or z's. So let's just choose to eliminate the y's. Oops. So we'll do 26 times a plus b. You guys all okay there? So I get 9z is equal to negative 18, or z is negative 2. Okay, once I have that, what do I do? Very good. Plug it back into some two-variable equation. I think you'd be crazy to pick anything other than equation A to plug that into. So there we have y equals 3. And we still have z equals negative 2. So then we take those two, and what do we do with those? Plug it back into one of the three variable equations. Again, I feel like you'd be crazy to pick anything other than equation C to plug that into. But it'll work, you know. It doesn't matter which one you plug them into. So then we have our answer, the ordered triple negative 8. I'm sorry, positive 8, positive 2, negative 3. Oh no, galloping goblins. I put these in the wrong spot. Confound it. Mr. Kulik, you are the dumbest piece of junk there ever was. Did anybody notice and not say anything?
Yeah.
Shame on you.
Say it and then be wrong.
Shame on you. Shame on you. That's okay. Shame on me. There we go. Blah! You know, sometimes it happens. Okay. I want to do one more example here of what can happen. And then we'll be done and do the homework quiz that you guys probably knew was coming. Sound good? All right. Is this going okay so far? Again, this is something you did last year, so it should be ringing some bells and shouldn't feel too unfamiliar. The one thing that I don't think we did last year was ask you to to do this when you get an infinitely many solution situation. Or this would be providing the general solution. All right. So here we have a system. A plus 5b minus 2c equals -1. Negative a plus negative 2b plus c equals 6. I'll just make that a minus sign there. I don't know why I wrote plus a negative. And then negative 2a minus 7b plus c equals positive 7. And we're asked to provide the general solution for this infinitely many solutions problem. Hi. So I don't know about you, but we're not told how we need to solve this, whether substitution or elimination. I think in general, elimination is probably a little easier for me. So that's what I'd prefer to do here. If I look at my variables, I think there's an obvious candidate of which one seems like the easiest variable to eliminate first. What do you guys think? A, B, or C? Which one seems like the easiest one to eliminate first? I would say A as well. Mostly because equations A and B are already set up, ready to go. And then since the coefficient on A is, for equation A is 1, there's not much I have to do to get it ready to add to C. Okay, so when I do each of these eliminations, I get a two-variable equation. I want to point out to you guys in an infinitely many solution situation or no solution situation, even at one of these steps, you could get the 0 equals 0 or the 0 equals 1 kind of thing to indicate that it's no solution or infinitely many solutions, but you don't have to. Now in this problem, we were told there was infinitely many solutions. And you see that when we create our new two-variable system, it's super obvious that there's infinitely many solutions here, right? How can I tell so easily that there's infinitely many solutions? Yeah, it's the exact same equation twice, right? Clearly, that has to be infinitely many solutions, right? We could go ahead and do the, solve that system by substitution or elimination, but I think in this case where they're exactly the same, there's really no point in doing that. You guys cool with that idea? However, we're going to ask you to do a little bit more in the three-variable situation when we run into an infinitely many solutions. Okay? So what we'd like you to do is to give us something called the general solution. So what the general solution is, it's like, okay, there's infinitely many solutions to this, but that doesn't mean any ordered triple you give me is actually a solution. What we want to do is we want to write an ordered triple in terms of either A or B or C that we can use to generate the infinitely many solutions. So I'll kind of show you how that works. So once we have a two-variable equation, we're going to take that and solve it for either, or get one of the two variables by itself. It doesn't matter which one you do. In fact, there's three versions of this answer that would be correct. One answer that involves just C's, one that involves just B's, one that would involve just A's. In this case, let's get the C by itself. It seems like that would definitely be the easiest route to go because we can avoid any fractions going on there, which again, if possible, that's what I would want to do. Everybody cool? So we'll subtract the 3b over and then divide by the -1. So what this says then is in my ordered triple, the C component, this is like my A, B, and C components, should be 3b minus 5. Because this component is in terms of B, the B component is just going to be B. It's just going to be itself. B is like the independent variable in a function. Everybody okay so far? So again, since this was C, I'm going to put that part in the C spot. Because it was in terms of B, I'm just going to put B in the B spot. All that I'm left to do now is to find A in terms of B. So to do that, I'm going to take this and surprise, surprise, I'm going to go plug this back into one of my three variable equations. I'm going to plug it into equation A, is the one I'm going to choose to use. The reason I'm choosing to use A is because the A coefficient is 1, so I know I won't have to do any division and create any fractions. Is everybody so far so good? And now I'm just going to go ahead and simplify and get the A by itself. So A equals B minus 11. So I'm going to take this and plug it back in here. In the A spot. So this is my general solution. Keep in mind that there's three different versions depending on what you chose to eliminate first and which variable you chose to get by itself. Your answer could be in terms of all A's or all C's also. There's three different versions, whether you answered it in terms of A, B, or C. On a test or a quiz or whatever, I would not care which one you did. I'd accept any of the three versions. So what this is doing is it allows us to generate answers. So for example, if I pick B to be 0, that would mean 0 minus 11, or negative 11, 0, and then 3 times 0 minus 5, or negative 5, would be a solution. And because I have infinitely many choices for B, I can generate infinitely many solutions to this system. So for example, then if I choose B to be 1, I'd have 1 minus 11 or negative 10, 1, and then 3 times 1 minus 5 or negative 2. And I could do this as long as I wanted, right? that okay? We see how this is, why we call this thing a general solution, because it basically gives us a map for generating the solutions to the infinitely many solutions to this system, really systematically. I just pick values for B and then plug that in, and I get a solution. I can give you as many as I want, or as you wanted, and just keep going, picking new values for B. You know what I mean? Okay. Let's stop here. At this point, you can now finish the problem set. So that would be, looks like 19 to 34 is the rest of things. Next time in class, we'll do we'll have our review day or whatever. And just like before, we'll let you make a half sheet of notes for the test, but you got to turn those in on the review day. If you happen to be absent or whatever, just email them to me. That's fine, as long as it's on that review day. Not a big deal. You can do it at home. Just take a picture or whatever. Everybody cool?
Yeah.
Okay. You ready to do this homework quiz then? Okay. Pencils and Calkies, and let's get this party started. Sure. You do have one, right?
Yes, I do.
Okay. I'm just checking. So just to point out, make sure you're looking at the directions and answering all the parts that we're looking for. So in problems 1 and 2. Oh, yeah, it's a good. Problems 1 or 2, I ask you to solve each linear system by graphing. I asked you to list the equations you entered into your calculator, sketch the graph from your calculator, and then list the solution. If there's not a unique solution, you should write either no solutions or infinitely many solutions, depending on which situation you ran into. And then for problem 3, again, it says solve the system of linear inequalities. Ask you to make sure you list the inequalities in slope-intercept form, graph each inequality, and clearly identify the overlap of the shaded regions. Pretty standard, but I figured I'd read the directions aloud because it's not like I ask you to do a lot of things in there. You know what I mean? But none of them are hard. Okay, I'm going to shut up and get out of your way now.